Hello everyone and welcome back to PostNetwork Academy. I am Bindeshwar and in today's lesson we will dive deep into an important concept in probability theory, the moment generating function of the binomial distribution. So let's begin with the definition. So the moment generating function of a random variable x is defined as moment generating function. You will write subscript t expected value of e raised tx, and then you can see that for a continuous random variable you will have integration multiplied by distribution function, and for discrete random variable summation, and e raised tx multiplied by probability distribution function. And if you expand t e raised tx, so you will get the following expression. This one you will get, and see that if you take expectation, so you will get that moment generating function. So e x square e x raised r. So these are moments about origin. So that is the first moment, second moment, and rth moment about origin. And see that how will we calculate. So basically, if we write using this expression, so we will get this one, where mu dash r is the rth moment about origin. So here, because it is called moment generating function because it generates moments. That's why name is simply moment generating function. But how will it get generated? So first of all, if you want first moment generating function, first moment, so you will differentiate moment generating function first time. I mean, you will put t is equal to 0. So for rth one, just differentiate r times and put t is equal to 0. You will get that moment. Moment. So for example, if you want to get first moment, so you will differentiate one time and you will put t is equal to 0. So you will get ex the same way, and here just I am again writing here because here again I want to show that suppose that I want first moment. So if I differentiate mx t, this I am keeping dash or prime, so I will get 1 not 1 e x, right, plus t 2t upon factorial 2 e x raised square plus, and all will have t term. So if I put t is equal to 0, that means mx prime t, here t is equal to 0. So definitely we will get here ex. You can do yourself, and if you put, that means differentiate it 2 times. So what will we get? So m x t dash I'm writing here. So I will get e x, right, here 2 t upon factorial 2 e x square, you can say that, plus here I'm not writing any term because I don't need that one, and that will contain t. Second time if I differentiate here m 2 times, so you can see that this will become 0, x you will write, and t is equal to 0. So that will become, you can say that 0, and here what you will get, e other term contain t, so that will become 0. So that will, you will get e raised x square. So this way you can get moments about origin. So what you have to do, you have to differentiate. If you want to third moment about origin, differentiate 3 times, and thereafter put t is equal to 0. So you will get moments, first moment, second moment, third, fourth, whatever you want. So that's why I wanted to explain in detail. And this way it has come. First moment, one time if you differentiate and put t is equal to 0, so you will get ex. That means expected value of random variable. That is mean basically. Now, moment generating function of binomial distribution. I started because I wanted you to recall. Now, let us see moment generating function of binomial distribution. So, because binomial distribution is a discrete distribution, so we will use summation here. So, moment generating function, so expected value of etx, as we have seen. Thereafter e raised tx, and basically what will we get here? We can rewrite here. You can see that q e raised t, that x, and p et n minus x. So again we can write when we combine, so basically you can replace by anything here, a and b. So and that is a binomial expansion. So you will write here a and b. That means a plus b raised n. So if you combine, you will get. So that is a moment generating function of binomial distribution here. That means moment generating function of random variable x. So using that generating function, moment generating function, we can get moments. So let us see. So here, just if you differentiate, I am leaving upon you that just differentiate moment generating function mxt one time and put t is equal to 0. So you will get this one. That means mu is equal to np you will get. The same way, differentiate that moment generating function 2 times. So what you will get? You will get basically here the term, and here is actually I have calculated variance. So variance requires here e x square minus e x the whole square. That is the variance. So basically this is np, and here how will you calculate? Just differentiate moment generating function 2 times and put t is equal to 0. So you will get this expression, and if you plug, you will get npq. So the same way you can get others if you want. And this is the moment generating function of binomial distribution, and this is one of the most important topic for many problems arises in probability distributions, or to find new distribution or to verify new distribution. Moment generating function is a key concept. So hope you have understood. For more resources, you can visit postnetwork.co. You can subscribe my YouTube channel to support me. Facebook page you can visit, LinkedIn page, and you can also visit GitHub repositories for coding like C++, Python, and machine learning, artificial intelligence, and even for statistics as well. So hope you understood and you will support me. Thanks for watching the video.